Title: A Model Generalization Study in Localizing Indoor Cows with COLO Dataset. Abstract: This study explores the generalization capabilities of YOLOv8 and YOLOv9 models for cow detection in indoor freestall barn settings. It focuses on varying training data characteristics such as view angles and lighting and model complexities. The cow's localization (COLO) dataset is leveraged to investigate three key hypotheses. 1. Model generalization is equally influenced by changes in lighting conditions and camera angles. 2. Higher model complexity guarantees better generalization performance. 3. Fine-tuning with custom initial weights trained on relevant tasks always brings advantages to detection tasks. Introduction. Object localization has become an essential task in precision livestock farming (PLF). This technique allows farm operators to manage animal well-being and health in real time, optimizing their resource management and improving sustainability. Object detection is the simplest form among these tasks, localizing objects of interest by enclosing them within a rectangular bounding box defined by x and y coordinates, pixel width, and pixel height. Successful instances in this category include YOLO, Faster RCNN, and SSD. These models have been adopted and applied by animal scientists for detection in precision livestock farming. Model generalization, pre-training, and fine-tuning. Implementing image-based systems in livestock production has become more common, but current studies primarily focus on accuracy in homogeneous environments and rarely address the challenges of model generalization. Good generalization performance ensures that the model can reproduce similar results as reported in the original study, even in new environments with different conditions. Factors such as camera angles and the presence of occlusions can impact generalization in the deployment environment. Fine-tuning is a common practice that involves adjusting the model's parameters to better fit the specific use case. This study's findings reveal considerable challenges in detecting cows in images taken from side views and underscore the importance of including diverse camera angles in building a detection model. Furthermore, the results emphasize that higher model complexity does not necessarily lead to better performance. The optimal model configuration heavily depends on the specific task and dataset, highlighting the need for careful model selection tailored to the particular application. Lastly, while fine-tuning with custom initial weights trained on relevant tasks offers advantages to detection tasks, simpler models do not benefit similarly from this approach. It is more efficient to train a simple model with pre-trained weights without relying on prior relevant information, which can require intensive labor efforts. YOLO family models and public datasets. The study explores the generalization of YOLO family models across varying environmental settings and model complexities within the context of indoor cow localization. The YOLO family models, including YOLOv8 and YOLOv9, are designed to perform object detection in a single pass through the network. They incorporate innovations like the C2F module, COLO activation, and an anchor-free approach, which support efficient feature pooling and multi-scale detection. YOLOv9 further addresses the information bottleneck issue through programmable gradient information (PGI) and the Generalized Efficient Layer Aggregation Network (GELAN), notably boosting inference speed and facilitating the detection of objects across varying sizes. The study also discusses the importance of public datasets in computer vision, such as ImageNet and COCO, which serve as benchmarks for image classification and object detection. However, these generic datasets may not be sufficient for specific use cases like livestock scenarios. Efforts have been made to create public datasets for livestock applications, including the Cattle iView dataset, the Pig dataset, and the Open Cows 2020 dataset, which support precision farming applications such as automated productivity assessment, health and welfare monitoring, and veterinary research. The study examines three hypotheses. 1. The generalization of YOLO family models across varying environmental settings. 2. The impact of model complexity on generalization performance. And 3. The effectiveness of fine-tuning pre-trained models on a new dataset. The findings of this study will provide insights into the suitability of YOLO family models for indoor cow localization and inform future research on more complex tasks in precision farming. This study delves into the generalization of computer vision models in cow localization tasks, focusing on the impact of lighting conditions and camera angles. The findings suggest that both factors equally influence model generalization, with higher model complexity guaranteeing better performance. Fine-tuned models offer persistent advantages over pre-trained models, especially when training sample sizes are limited. A new dataset, COLO, is being developed to facilitate these investigations and provide practical guidelines for precision livestock farming researchers deploying CV models. The study involved 100% Holstein cows housed in a freestall barn with automatic fans for heat stress management. Cows were milked twice daily, fed ad libitum, and manure was removed regularly. Images were collected using Amazon Ring cameras installed at different heights and angles, capturing various perspectives and lighting conditions. The dataset was manually curated for quality, comprising 504 images from the top view camera, 500 from the side view camera, and 250 from the external camera. Images were categorized based on lighting conditions, with examples shown in Figure 1a. Image annotations were conducted using an online platform, RoboFlow, to define cow positions in the images. Bounding boxes were manually drawn to enclose cow contours, providing coordinates and dimensions. If cows were partially occluded, invisible parts were inferred based on adjacent visible parts. If a cow's position was too far from the camera, making important body features unrecognizable, the cow was excluded from the dataset. Final annotations were saved in the YOLO format, with one row per cow in the image. The study explores the generalization capabilities of YOLO models in detecting cows under various environmental conditions and camera angles. The COLO dataset, comprising images from different viewpoints and lighting conditions, was used for model training and evaluation. The model's performance was assessed using metrics such as precision, recall, mean average precision, MAP, at an IOU threshold of 0.5, and averaged MAP at varying IOU thresholds. In Study 1, a cross-validation strategy was employed to compare the performance drop between different view angles and lighting conditions. 5 training configurations were designed: baseline, top to side, side to top, day to night, and external. The YOLOv9 model was used as the base model for this study. The results showed that the model's performance decreased when trained on one dataset configuration and tested on another, highlighting the challenge of generalizing to unseen conditions. In Study 2, the correlation between model complexity and performance was investigated by examining 5 YOLO family models: YOLOv8n, YOLOv8 meters, YOLOv8x, YOLOv9c, and YOLOv9e. These models differ in their depth multiplier, width multiplier, and ratio factor, which determine their parameter counts and computational efficiency. The study found that model performance generally increases with model complexity, but the improvement may not always be significant, suggesting that model selection should consider both accuracy and computational efficiency. Overall, this research provides insights into the challenges and opportunities of using YOLO models for cow detection in various environmental conditions and camera angles. It emphasizes the importance of considering model complexity, generalization capabilities, and computational efficiency when selecting a model for specific applications. This study explores the generalization capabilities of YOLO models in detecting cows from different camera angles and environmental conditions using the COLO dataset. The dataset consists of 8 configurations, including baseline, top view, side view, external, and various combinations of these. The models were trained on different sample sizes, and their performance was evaluated using MAP at 0.5:0.95, MAP at 0.5, precision, and recall metrics. The results show that the baseline configuration achieved good generalization capability with over 90% of the predictions correctly positioning cows at the 50% IOU criterion, MAP at 0.5. However, the performance significantly varied across different camera angles and environmental conditions. For instance, the top 2 side and side 2 top configurations exhibited lower MAP at 0.5:0.95 values compared to the baseline, indicating a decrease in model performance when transitioning between top and side views. The study also investigated the relationship between model complexity and time consumption. It was found that as the model complexity increased, so did the time consumption for both training and inference. This trade-off between model performance and computational cost is crucial for real-world applications where computational resources are limited. Furthermore, the study assessed the advantages of using fine-tuned model weights over pre-trained model weights as initial weights. The results suggest that fine-tuned models with specific initial weights can outperform pre-trained models, especially when the training sample size is small. However, as the sample size increases, the performance gap between fine-tuned and pre-trained models diminishes. In conclusion, this study highlights the importance of considering camera angles, environmental conditions, and model complexity when developing object detection models for specific applications. The COLO dataset provides a valuable resource for researchers to evaluate and improve the generalization capabilities of their models in detecting cows under various scenarios. This study examines the generalization capabilities of YOLOv8 and YOLOv9 models across various model parameters and data configurations, utilizing the COLO dataset. The results indicate that higher model complexity does not necessarily lead to better performance, as the optimal model configuration depends heavily on the specific task and dataset. In some configurations, simpler models performed better, while in others, larger models excelled. The study also found that the training configuration significantly affects the relationship between model complexity and performance. Furthermore, the study highlights the importance of considering the specific characteristics of the task and dataset when choosing a model, rather than defaulting to more complex models under the assumption they will perform better. A small model such as YOLOv8n can yield 90% accuracy with a relatively small size of training samples, indicating that deploying a small model is optimal in balancing computing time and prediction accuracy for simple and homogeneous tasks like positioning cows. Additionally, the study reveals that the benefit of using fine-tuned initial weights is minimal for simpler models. For larger models, however, utilizing weights previously fine-tuned on various data configurations can leverage additional learned features and adaptability, resulting in better performance even with a small amount of new data. The analysis also provides insight into performance across homogeneous viewpoint data configurations, with the top view camera configuration consistently yielding higher map values due to an unobstructed aerial perspective. The study also evaluates computational resource requirements for various YOLO models, including training time, inference time, and model weight sizes. The findings show that using larger models, such as YOLOv8x, which has 20 times more parameters, increases training time by 4 to 6 times, depending on the training sample size. Additionally, YOLOv9 models generally require more training time and have slower inference frames per second compared to YOLOv8 models. Inference time was measured as the average FPS in a batch of 64 images, with the smallest model, YOLOv8n, on a CPU being slower than the largest model, YOLOv8x, on a GPU. High FPS models are essential for real-time inference, which usually requires a model with an FPS higher than 30. The results indicate that implementing YOLO models on a CPU may not meet real-time requirements, especially for larger models. Lastly, model weight sizes were considered, impacting memory requirements and deployment feasibility, especially in edge computing environments. The weight sizes and parameter counts of various YOLO models are displayed in Figure 7c. In conclusion, this evaluation highlights the trade-offs between model complexity and computational efficiency. The larger YOLO models, while offering potentially better performance, require significantly more computational resources. This analysis helps researchers and practitioners select the appropriate model based on the available computational resources and the specific requirements of their application. This study examines the impact of various training configurations and model complexities on the performance of YOLOv8 and YOLOv9 models for cow detection in indoor farm environments. The results indicate that model performance is highly dependent on camera viewpoints, with side views presenting the greatest challenges. Fine-tuning models with weights from similar datasets substantially enhances performance, particularly for complex models in scenarios with limited data. The study also introduces a public cow localization dataset, COLO, to support the research community. The findings suggest that while increasing model complexity can improve performance, this is not always the case, especially in challenging configurations like top-to side, which predict images from a side view using a model trained on top-view images. Models trained on a single viewpoint exhibit limited generalization, underscoring the importance of incorporating diverse and consistent camera angles in the training data. The paper discusses a model generalization study using the COLO dataset, focusing on the application of deep learning models in precision livestock farming. It highlights the importance of object detection and segmentation in animal farming, particularly for tasks such as posture detection and tracking of individual animals. The authors emphasize the need for robust and efficient algorithms that can handle large datasets and provide accurate results. The study utilizes various state-of-the-art object detection models, including YOLOv8, SSD, and FCOS, to evaluate their performance on the COLO dataset. The dataset consists of images collected from various farms, featuring different breeds and ages of cows in various environments. The images are annotated using tools like LabelMe and CVAD, with a focus on keypoint detection for accurate animal identification and tracking. The paper also explores the use of transfer learning and fine-tuning pre-trained models to improve performance on the COLO dataset. It discusses the importance of model selection, hyperparameter tuning, and data pre-processing steps to achieve optimal results. Furthermore, it highlights the potential applications of these models in real-world scenarios, such as monitoring animal health, detecting abnormal behaviors, and optimizing feeding strategies. In addition, the paper reviews recent advances in deep learning architectures, including ResNet, UNet, and their variants, which have shown promising results in various computer vision tasks. It emphasizes the importance of understanding the trade-offs between model complexity, computational cost, and performance when selecting a suitable model for a given task. Overall, the paper provides a comprehensive overview of the current state-of-the-art in object detection and segmentation models, their applications in precision livestock farming, and the challenges associated with working with large datasets in this domain. It serves as a valuable resource for researchers and practitioners working on similar projects, offering insights into best practices, model selection, and potential future directions for improvement. This study delves into model generalization using the COLO dataset, with a particular emphasis on hyperparameter tuning for optimal performance. The authors leverage the Ultralytics library and provide a comprehensive table detailing the hyperparameters used in their training procedure. These include parameters such as epochs, batch size, optimizer, and various image augmentation techniques like altering hue, saturation, brightness, translation, scaling, flipping, mosaic creation, mix-up, and copy-paste. The hyperparameters are set to specific values: 100 epochs, a batch size of 16, an auto-selected optimizer, and various fractions for image augmentations. For instance, the hue value is altered by 0.015, saturation by 0.7, and brightness by 0.4. The images are randomly translated by a fraction of 0.1, scaled by 0.5, flipped horizontally with a probability of 0.5, combined into mosaic images with a probability of 1.0, mixed up across multiple images with a probability of 0.15, and copied and pasted across images with a probability of 0.3. These hyperparameters play a crucial role in enhancing the model's generalization capabilities on unseen data. By carefully tuning these parameters, the authors aim to achieve better performance and robustness in their model. This appendix provides valuable insights into the experimental setup and can serve as a reference for future studies focusing on model generalization and hyperparameter optimization.